In this tutorial, I'm going to show how to do simple optimizations. You can add an optimizer block from the Mason library, and in here we have the controls for the optimizers. You can run genetic optimizers. There's a simplex. Simplex is a nonlinear gradient search, and then we throw in a default argument here. Now I'm going to turn off the simplex optimizer, so I don't have any of these optimizers turned on right now. So I can just run this, run Mason, and see that we ran without error, and throw a plot of what we expect. So in here, for the transmission line, for my little Wilkinson circuit here, I have a little Wilkinson divider, and I've put in the correct values, but I've also added this little optimizer snippet. It's actually a little XML tag that you can add in with a little semicolon after it. Now, if you want, you could actually replace the semicolon with a colon, and it'll show the tag. Generally speaking, I like to have a cleaner schematic, so I usually leave those invisible. If you want to turn off the tag, you can also just put no opt instead of having that opt tag there. But here what I've done is I've set up a minimum value that the impedance is allowed to take, a maximum value, and I've defined a step. So it's allowed to, when it optimizes, be 70.7, or it could be 70.78, sorry, 70.8, but it's not allowed to be 70.78 or 70.71 because it has to be in a 0.1 step. The electrical length I've set up to be a minimum of 45 and a maximum of 180, but I haven't actually set a step, so it could be anything that it wants that's a valid floating point number between that value. I'm not going to optimize the center frequency because with the electrical length that would be redundant. You can have units, by the way, with the min and the max, but here you know, the default is degrees, but you know, if you wanted, you could stick degrees, or if it's a length, mils or inches or whatever. So we're going to take a look at the resistor, and here I've set up a minimum and a maximum and a step of 1 ohm, so it's allowed to step that between 50 and 200 and 1 ohm increments. So now what I'm going to do is I'm going to accidentally hit the zoom button. I'm going to spoil the values here so that my optimizer will have something to do. It will start the optimization with the original values, and it won't just start from scratch. So if you're running subsequent optimizers, you're not going to lose anything. And let me turn on my simplex. I'm going to go ahead and turn on the genetic optimizer to give me some randomness. Simplex falls prey sometimes to finding local minimums, so you want to either use a random or genetic optimizer to start out with. You can do a search on the wiki to see more about the different optimizers and the different options that they have. I'm not going to cover that all here. I'm going to add 2 more arguments. Right now I have an argument set up for the match, but I also want to set up something for the through and for the isolation. Now, like we had for my optimization arguments, I also have minimum and maximum values that I allow for my figure of merit to be. This calculation is added to some error function, and I'm going to seek to minimize that error function. Whatever that calculation deviates from the error function is going to be what we're trying to use. So if I have a minus 3.01 dB through characteristic, then it's going to score 0 on the error function. Anything that deviates from that, it's going to try to penalize. So at this point, I think I can run my optimizer. It's trying to optimize over the whole band here. And obviously this circuit is not going to be able to do that. So if I hit U to update, it's given me some values. Its best ability to try to minimize the error function that I've created. Let me go ahead and shift this up. In the GUI, the order that you put these optimizers at doesn't really matter. It only pays attention to the order they are in the toolbar. Let me just reorder this a little bit. All right. So I just tried to optimize over the entire band, and it's not going to be able to do that effectively. So one thing I could do is I could try to change the frequency that I'm running the simulation at, narrow that down so that my optimizer can work more effectively. Because really all we're trying to do is improve the Wilkinson, ideally at like the 1 gigahertz is what I'm going to pick. So instead of changing that, because it's a relatively fast run, I'm going to set up frequency start and frequency stop. I'm going to shift and arrow over to copy paste this. So these calculations can be set up to only work in a certain range. So if you're working on a filter, for example, you can set up a frequency start and stop for some parameter at the low end or at the high end or in the mid band, so you can have multiple optimizations, multiple calculations that feed into your error function that are at different frequency bands. So now when I run Mason, you'll notice that the error function is a lot lower, and it's actually zeroed out. Now that doesn't necessarily mean that what we have is what we want. What we'd like is something that's more like the 70.7 ohms and the 90 degrees. But you notice that the electrical lengths here are different, the impedances are different. What it's done is, at 1 gigahertz, it's set up the -3 dB, and it's set up a match and an isolation that are less than the -15 dB that I gave it. But really, for this ideal circuit, I could tighten up the specs. A lot of optimization, the art for optimization, is about being intelligent about setting up your parameters. So for one, setting my allowable units, allowable range for the acceptable performance, that's part of it. Another part for this is that really I know that the impedance for this transmission line and this transmission line should be the same. The electrical length should be the same. So I'm going to add a little bit more intelligence. I'm going to use a variable block, and I'm going to just create a new variable, just to save myself some typing, Z1. And Z1, I'm going to have the same sort of optimization snippet. It's basically a little XML snippet for optimizing, where I have a minimum between 50 and 100 ohms again, same step. And I'm going to set up same thing for the electrical length. And instead of directly defining my Z0, I'm going to set it to be equal to that variable. Alright, so now I've set up my transmission lines to both have the same impedance and electrical length. So now when I run Mason, my error function is higher than my initial run because I changed my maximum allowed match and isolation to be -50 dB, but you can see that it's driving it back down to 0. So now if I update and save, I have the 70.7 ohms and the approximately 90 degrees that I really wanted. Now let's say, for the sake of argument, that you perform an optimization, but you've done something that is very wrong. I'm going to set up the wrong minimums, run Mason, and I can tell just by looking at this that, something's not right. Well, historically I've been hitting this S button to save the optimized Mason values, but instead of hitting this S button, if I wanted to go back after updating, what I can do is I can just go to my file and load up that old Mason file, because whenever I run the optimizer, what I've actually been doing is I've been creating a new design file, new TinyCAD design file, and when I hit U, I've been loading that file up. When I hit S, I've been saving that file, and I can always just load up the old file before I hit S in order to go back. One other thing, let's say that we wanted to turn off one of our components. So we've shown how you can turn off different optimizers. You can actually turn off certain calculations. We've shown how you can turn off certain parameters from optimizing by making it a no-opt command. But what we haven't yet shown is how to turn off a component. You do that by turning off the reference designator. So without having to delete this component, I can turn it off. I can see that this is the plot with the resistor still on there, and I'm going to run Mason where I've turned off that resistor, and now I no longer have that isolation component. So what I should see is my isolation creep back up.